Safety, quality, and productivity are the concerns of every industry. From the plants that produce our paper products to the companies that manufacture precision machine tools, all are affected by safety, quality, and productivity. Modern industries depend on the ability to measure and control scores of variables that directly affect plant safety, product quality, and operating efficiency. All major industries, from the automotive and aerospace to the food and drug industries, rely on precise and reliable control systems. Production systems and their equipment vary greatly from one industry to another, and so do their control systems. A nuclear power plant must pay particular attention to plant safety, as must a steel mill. A pharmaceutical company must maintain rigid quality control to ensure pure and safe products. These and other industries each have dozens of different production lines, with rigid specifications for each and every product, requiring close control of many variables. In all industries, whether a plant is large or small, the measurement and control of manufacturing variables is the key to successful operations. The systems controlling these variables are known as automatic control systems. The program, Basic Automatic Process Control, showed how a small chemical company used control systems to maintain the quality of its product while increasing production. Let's look at the manufacturing process and control systems it used. The company's chief product was a specially blended liquid, which was sold in bottles. Raw materials were mixed in an inline mixer and passed through a heat exchanger, where the mixture was heated with steam to 80 degrees. This was the temperature required to ensure proper blending of the ingredients. If, for some reason, the temperature rose above 85 degrees, one of the ingredients became overactive and the product was off specification. On the other hand, if the mixture was allowed to cool below 75 degrees, blending was incomplete, and the product had to be reprocessed or thrown out. In short, good product quality required that the temperature be maintained at 80 degrees, plus or minus 5 degrees. After leaving the heat exchanger, the blended product then flowed through a pipeline to 2 automatic bottling machines. Temperature control was first attempted with an on-off controller, but on-off control quickly proved to be totally inadequate for the continuous process. The company then installed a proportional-only controller. The gain of the controller was adjusted so the control valve admitted the right amount of steam to the heat exchanger to maintain the desired temperature. This controller worked well until one of the bottling machines was started or stopped. These load changes to the system created temperature offsets, resulting in a loss of product due to temperatures that were either too low or too high. An integral unit was then added to the controller. By responding to the duration of the temperature error, the integral unit detected that the error was still present sometime after the load change. The signals from the integral and proportional units combined to correct the error or offset. Although the proportional integral controller worked well to eliminate offsets, its output signal did not react quickly enough to reposition the valve during sudden load changes. Each time a bottling machine was started or stopped, some product was lost. A derivative control unit was then added to the controller. This unit could detect the rate of temperature change and cause additional valve movement whenever the temperature changed rapidly. The control instrument finally used in the plant was a 3-mode controller known as a PID controller. It contained proportional action, which responded to the size of the error to maintain the system under most conditions; integral action, which responded to the average error over a period of time to compensate for load changes; and derivative action, which responded to the rate of change in the error signal to speed up valve action when fast load changes occurred. With the PID controller, the temperature of the product in the heat exchanger was maintained within the required limits. The control system enabled the company to keep the high quality of its product, while it increased production by adding more production lines. The story didn't end there, however. The product was so successful that soon other companies began producing and selling competitive products, and some of the competing products were priced below that of the original. The company projected an increasing market for the product and didn't want to lose its share of the market. So it decided to look for ways to reduce production cost without lowering its high-quality standards. The analysis of production costs showed that there were two areas in which the company might be able to save money: raw materials and energy. Since raw materials accounted for a major part of production costs, they focused their attention on reducing materials costs. Management quickly spotted two possibilities. First, they could use lower grade and therefore cheaper raw materials. But lower grade materials could lower product quality, so this suggestion was quickly vetoed. Second, they found they could save money by eliminating the intermediate producer of one of the raw materials from the supply system. This was their rationale. The company's product was made of two components, A and B. These came from two different suppliers, and they were mixed together in a blending tank before being added to the continuous reactor. Component A, however, was itself a mixture of two other ingredients, which an intermediate producer combined and sold by the tank load. If the company could make this mixture in-house, it could eliminate the extra money spent on expenses for the intermediate producer. The recipe for making component A was simple. It required 2 parts of one ingredient for each part of the other, a 2-to-1 ratio. Because the recipe was so simple, eliminating the middleman in the supply chain meant that only a minor modification to the plant was needed. This is what the modification looked like. An additional pipeline was installed that intersected with the line that formerly carried component A into the mixer and heat exchanger. The two ingredients were then mixed together in the pipeline to form component A. The only problem was that the plant had to somehow make sure that twice as much of the second ingredient always flowed into the pipe's intersection. A ratio controller was used to make sure that happened. Ratio control can be accomplished by controlling both streams, or by using one control stream and one uncontrolled stream. When using an uncontrolled stream, only one of the two flows entering a system is controlled by a ratio controller. It doesn't matter if the other flow varies, so this uncontrolled stream is known as the wild stream. In ratio control, the only thing that matters is that the control stream matches the wild stream in the desired ratio. In this case, the volume of product in one stream must be twice as much as in the other. Ratio control is a lot like staying comfortable in a shower. Both hot and cold water valves are opened and then adjusted to produce the desired water temperature. But if someone in the next apartment turns on the cold water, the flow of cold water into the shower suddenly decreases. To avoid scalding himself, the bather quickly reduces the flow of hot water into the shower head. In effect, he is trying to maintain the proper ratio of hot to cold water. A ratio control system accomplishes a similar adjustment automatically by using two sensors, a ratio controller and one valve. A sensor in the wild stream transmits a signal proportional to the flow rate to the ratio controller. The flow rate in the controlled stream is compared to the flow rate of the wild stream, and the ratio controller maintains the controlled flow rate to give the desired ratio for the mixture. This desired ratio is determined by adjusting the set point on the ratio controller. A high ratio means that the difference in the flow rates is great. A low ratio means that the difference is smaller. Here is how ratio control worked in the chemical plant. The flow of ingredient 2 into the process was continuous but variable. The flow of ingredient 1, however, was carefully controlled so that its flow was always half that of ingredient 2. For the ratio to be controlled, it really didn't matter what the absolute flow rate of the materials into the process was. It only mattered that this 2-to-1 ratio was always maintained. The addition of the new ratio controller and an additional pipeline was not a very costly modification to the plant, and soon the company was enjoying the benefits of reduced materials costs. However, energy was another major concern. since energy costs were an appreciable portion of the total production costs. This made the cost of producing steam for the process a major expense, so the company next turned its attention to reducing energy consumption. Although the potential savings were not as great as those achieved in materials costs, the plant engineers knew they could conserve energy if they could reduce the amount of steam needed in production. One way to reduce steam requirements would be to lower the set point of the product temperature. However, this could only be done if the variations in temperature could be reduced. This temperature record shows why. First, the temperature record shows that the product temperature varies plus or minus 5 degrees. The set point is 80 degrees, and the temperature can go as low as 75 degrees without affecting product quality. But if the temperature could be controlled at plus or minus 2 degrees, the set point could be lowered from 80 degrees to 77 degrees. Product quality would not be affected, since the temperature would not fall below the lower limit of 75 degrees. The plant engineers knew they could conserve energy and reduce costs if they could maintain the temperature in the heat exchanger at 77 plus or minus 2 degrees. Before they could do this, they needed to know what caused the temperature to change as much as it did. Here is what they found out. The heat exchanger used in the process was a typical shell and tube type, in which the product flowed in tubes through a steam jacket or shell and was heated by steam within the shell. The main cause for temperature variation was changes in pressure of the steam supply. As steam pressure increased, steam temperature also increased, and as pressure dropped, temperature dropped. Pressure changes occurred when other production lines in the plant increased or decreased their use of steam. When other lines decreased their use, the pressure of the steam supply increased. The temperature of the product began to rise, but it took some time for this temperature increase to travel through the mixture to the temperature sensor. By the time the sensor reflected the rising temperature, the temperature of the product was above the set point. The PID controller could maintain the temperature at plus or minus 5 degrees, but the delay in the transfer of heat prevented it from controlling the temperature more precisely. What was needed was a new way of controlling the temperature, a way that could respond more quickly to changes in the conditions that cause changes in the product temperature. This meant finding disturbance variables in the production system that quickly reflected these changes. This turned out to be the shell pressure in the heat exchanger. Here is why. Maintaining the product at set point required that steam be supplied to the heat exchanger at a constant rate. If the pressure of the steam supply fell, then the quantity of steam had to be increased to compensate. The pressure of the steam in the heat exchanger would change rapidly if there was any pressure change in the steam line. The steam pressure in the shell was the variable they chose to monitor in a control system that would respond quickly to changes in the steam supply. The engineers felt that this was an ideal situation for cascade control. Cascade control involves using the output of one controller to provide an input to adjust the set point of a second controller. This second controller is part of a feedback loop inside the feedback loop for the primary variable. A simple block diagram illustrates this concept of installing one feedback loop within another. The inner feedback loop is known as the secondary loop. In this loop, a variable, known as the secondary variable, is monitored and controlled just as in any basic feedback control system. The outer feedback loop is known as the primary loop, and in this loop, the primary variable is monitored. However, instead of directly affecting a final control element, the output of the primary controller is used to adjust the set point of the secondary controller. Here is how the chemical company used cascade control to keep the product temperature closer to the set point. The steam pressure in the heat exchanger shell was monitored, since it rose or fell almost immediately if there was a change in the steam supply. The output of this pressure sensor went to a controller that caused the steam valve to open or close in proportion to the shell pressure. This was the inner or secondary feedback loop. The outer or primary feedback loop still responded to the temperature of the product in the heat exchanger. However, instead of directly positioning the steam valve, the output of the primary controller was used to adjust the set point of the secondary controller. The secondary controller then positioned the valve. Under most circumstances, the secondary loop was doing most of the work involved in maintaining a steady product temperature. Its major responsibility was to minimize disturbances in the steam line. In contrast, the primary loop's major control action occurred whenever there was a disturbance or load change in the product, for it was then that the set point of the secondary controller had to be changed. Here is how the product's temperature record looked after cascade control was added to the system. Once each controller was tuned to the system, the temperature varied only 2 degrees above and below the set point, instead of 5. This allowed the set point to be lowered to 77 degrees and still keep the temperature above the lower limit of 75 degrees. The result was a reduction in the amount of energy needed to run the plant, and therefore a savings in the cost of making the product. However, while most of the company's engineers had turned their attention to saving energy, one enterprising young engineer had not. He was looking for further reduction in materials costs and was concentrating on component B. For this component, a precise pH value was necessary for good product quality. pH is a measure of the acidity or alkalinity of a substance. For component B, the ideal pH was 6.3, but a pH in the range of 6.2 to 6.4 was acceptable. If the material was too acidic or had a pH lower than 6.2, the product would become lumpy. If it was too alkaline or had a pH higher than 6.4, the product would separate into layers after it was bottled. The supplier of component B had provided it within the acceptable range. But the enterprising young engineer soon found out it would be far more economical for the company to buy raw material with a pH in the range of 6.2 to 6.8. All that was needed was a way to lower the pH when necessary. He determined that this could be done quite easily. First, a standard pH instrument could be used to determine the exact pH of component B. Then, if the pH was above 6.3, an acid could be added until the pH registered 6.3. Since the acid required was quite inexpensive and only small amounts would be needed anyway, the company would be able to pay off the cost of minor plant modifications quickly. The modifications needed required a control system to monitor and adjust the pH of component B. Once the president of the company heard about this opportunity to make further savings in materials costs, he quickly approved the plans for modifying the plant and the supply of component B. The control system the company chose as part of this modification was a feed-forward control system. In feed-forward control, a disturbance is detected before it has a chance to affect the process, and corrective action is taken before the disturbance creates an upset in the process. This type of control is known as feed-forward because it takes corrective action before a disturbance affects the process. In contrast, feedback control takes corrective action only after a disturbance is detected in the process. Feedback control is something like driving a car down the road by looking only through the rearview mirror. After the car has bounced off a curb, the driver turns the wheel after observing what he has just hit. Feed-forward control is more like the usual manner of steering. Objects can be dodged before a collision occurs, since they are spotted through the windshield. In the chemical plant, raw material was going to be accepted with a pH in the range of 6.2 to 6.8. The process required the pH to be between 6.2 and 6.4, so any variation in pH above 6.4 was a disturbance to the system that had to be corrected by adding an acid. With feed-forward control, it was possible to monitor the disturbance variables before they entered the reactor. A pH instrument was used to monitor pH, and a flow sensor was used to measure the flow. The feed-forward controller calculated the amount of acid needed to control pH at a desired value based on flow and/or pH disturbance. The output of the feed-forward controller positioned the valve to admit the required amount of acid to the stream to maintain the pH. In this configuration, when the pH of component B was 6.4, only a small amount of acid entered the flow. When the pH was 6.6, acid entered the flow at a greater rate. And when the pH was 6.2 or 6.3, no acid was added. Also, when the flow rate changed, the amount of acid added was adjusted to accurately maintain the pH. For 2 days after startup, the new system performed exactly as planned. The pH sensor worked, the flow sensor worked, and the valve adding acid opened and closed as necessary. The quality of the finished product was as high as ever. But on the 3rd day, something went wrong. The product bottled that day stratified or separated into layers. That meant the product was too alkaline, which in turn meant that not enough acid had been added to maintain the pH level. Worst of all, it meant that the entire day's production had to be thrown out. The plant foreman tried to find out what had happened. In the first 2 days, the pH varied between 6.3 and 6.6, and acid was added in the correct amounts to adjust the pH to 6.3. On the 3rd day, however, the pH varied between 6.6 and 6.8. Even more acid had been added than on the previous days, so there appeared to be nothing wrong with the feed-forward controller. But somehow this increased amount still wasn't enough to bring the pH down to 6.3, or even to an acceptable 6.4. The company president was not pleased with the young engineer or his bright ideas. So the enterprising young man consulted the company chemist, who quickly explained what went wrong. The concentration of the acid additive varied. There was no way to account for the variation, so a change in the acid concentration resulted in a pH level that was out of specification. The numbers used to describe the acidity or alkalinity of a substance follow an ordinary number scale, ranging from 1 to 14. This would lead one to expect that a substance of pH 2 would be twice as alkaline as a substance with a pH of 1. But in fact, the substance with a pH of 2 is actually 10 times as alkaline as the substance of pH 1. Each number on the pH scale indicates a 10-fold change in the acidity or alkalinity. A graph of pH and the amount of acid needed to neutralize it then looks like this. This graph shows a curve rather than a straight line. Between pH values of 6.3 and 6.6, the curve is fairly straight and flat. Between the pH values of 6.6 and 6.7, however, the curve begins to rise more steeply, and it continues to rise steeply up to pH 6.8. Because this graph does not follow a straight line, neutralizing pH is a non-linear process. What had happened in the plant was that the controller worked well to add the correct amount of acid based on the pH of the raw material and the flow rate. But the raw material was still more alkaline than the specifications allowed, even after the acid was added. This was caused by the variations in concentration of the acid additive, which was a disturbance variable that was not measured in the feed-forward system. There was no signal to the feed-forward controller indicating that the pH of the mixture was still too high. Fortunately, there was a way to solve the pH problem. This was done by adding a feedback control loop to measure the pH of the product in the mix tank and make additional adjustments if required to bring the product to specification. The feedback loop included an adaptive controller to correct for non-linearities in the disturbance variable. An adaptive controller was used since pH response is non-linear, and an adaptive controller can automatically adjust its response to compensate for non-linearities in a system. The addition involved adding a second pH instrument downstream of the mix tank and an additional acid supply line. If the concentration of the acid additive decreased, the feed-forward controller could not detect the decreased concentration and adjust to add additional acid to compensate. However, a downstream pH instrument would detect a pH error. The error signal caused the adaptive controller to adjust its action based on the size of the error and position the valve in the second supply line to add enough acid to compensate. Acid entered the mix tank in greater volume until the error was corrected. Some years ago, this would have meant that a plant operator would have to continuously monitor the pH and then adjust the controller whenever the pH went over 6.4. But now, with the aid of microelectronics, it's possible to use controllers that will automatically adjust gain, reset, or rate to compensate for non-linearities. The controller contains a small computer, which is programmed to change the controller's response when an error is not corrected at the current setting. Because the controller adapts its response to a change in conditions, it is known as an adaptive control system. Adaptive control is typically used in situations where the process gain is non-linear, just like our example of a pH process. In practice, feed-forward is rarely used alone because there is no means of verifying that it is performing as desired. In the chemical plant, a feedback loop with adaptive control was added to monitor the pH and compensate before a variance could introduce a disturbance in the process. Feed-forward control maintained the pH at the proper value most of the time, but the feedback control loop was needed to correct for any deviation in the required pH. We've now seen how the chemical company's control systems have evolved along with changes in the production system and, indeed, along with changes in the business environment. These systems have evolved from the basic feedback system using a PID controller to include entirely new control concepts. First, with ratio control, input from one flow stream was used to adjust another flow stream, maintaining a constant ratio between the two streams. Second, with cascade control, two feedback loops, one within the other, were used to minimize temperature variations. Third, with feed-forward control, disturbances in pH were compensated for before they had a chance to affect the system. And fourth, with adaptive control, a controller adjusted its response automatically to compensate for non-linearities in the process. With the help of these new control concepts and their respective control devices, production was maintained with consistent high quality, and the plant maintained product quality at a high level of productivity with a considerable cost savings. The chemical company was again outpacing the competition in sales. Other companies are likewise enjoying the benefits of advanced control systems. Whether it is the ratio of decongestants to antihistamines being made into cold medicine, the pressure and temperature in a nuclear reactor core, or the amount of bleach added to paper pulp. These and other manufacturing variables are controlled with advanced systems similar to those we've seen in our example. In any case, whether a plant's control systems involve ratio, cascade, feed-forward, or adaptive control, these advanced control systems play a major role in promoting safety, quality, and productivity.